Tonight, we're going to explore one of the strangest mysteries in modern astronomy. Just 4.3 light-years from Earth sits Alpha Centauri, the closest sun-like star system to our own. For generations, astronomers have treated it as the most familiar address beyond the solar system, the place we would visit first, the place we thought we understood best. But when the James Webb Space Telescope turned toward Alpha Centauri, something unexpected happened. A possible planet appeared near the system's brightest star. Then it disappeared. Follow-up observations failed to find it again. The closest sun-like star in the sky had suddenly become more mysterious, not less. And the very brightness that makes Alpha Centauri easy to see may be the thing preventing us from discovering what is actually there. By the end of tonight, you're going to understand why this candidate planet appeared and disappeared, how the closeness of a star can become the very thing that hides its worlds, and what Alpha Centauri's silence reveals about the limits of human seeing. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Alpha Centauri sits at the edge of everything familiar and the beginning of everything unknown. It is 4.3 light-years from Earth. That number is small only by astronomical standards. Light, moving at 186,000 miles per second, needs more than 4 years to cross that distance. A spacecraft traveling at the fastest speed any human-made object has ever reached would need roughly 70,000 years to arrive. In every practical sense, it is unreachably far. And yet, by the standards of the galaxy, it is the next room over. Here is what most people assume when they hear the name. A single bright star, the nearest neighbor, the obvious destination. But here is what it actually is. A triple system. 3 stars bound together in a gravitational architecture that most people who recognize the name have never pictured. Not one object. 3. 2 of those stars, Alpha Centauri A and Alpha Centauri B, orbit each other in a tight gravitational embrace. They complete one full orbit around their shared center of mass every 79.9 years. At their closest approach, they pass within 11 astronomical units of each other. An astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. So 11 astronomical units is roughly the distance from our Sun to Saturn. At their farthest separation, they pull apart to about 36 astronomical units. That is roughly the distance from our Sun out to Pluto. 2 stars dancing between the scale of Saturn's orbit and the edge of the solar system endlessly, once per human lifetime. And then there is the 3rd star. Proxima Centauri orbits the A and B pair at a staggering distance, roughly 13,000 astronomical units. That is about 1/5 of a light year from the central pair. A distance so vast that Proxima requires more than 500,000 years to complete a single orbit. To put that in perspective, that is longer than our species has existed on this planet. Proxima has not completed even one orbit since the first Homo sapiens walked the Earth. But here is where it gets strange. Proxima's grip on the central pair is extraordinarily weak. For decades, astronomers debated whether Proxima Centauri is genuinely bound to A and B, or whether it is simply a wandering star that happens to be passing nearby on a cosmic timescale. Some models suggested it might be drifting free, unanchored, a stellar neighbor by coincidence rather than gravity. Current evidence leans toward gravitationally bound, but barely. Think of a distant suburb connected to a city by a single crumbling road. Proxima clings to the system rather than belongs to it. One slightly different velocity, one ancient gravitational nudge from a passing object, and it might have drifted off entirely. The question is not fully closed. What Proxima is, definitively, is close. Closer than A and B, in fact. At 424 light-years compared to the 4.3 light-years of the main pair, Proxima Centauri is technically the nearest individual star to our solar system. It holds that record, but it earns no headlines for it. Proxima is a red dwarf, small and faint, burning at a fraction of the sun's output. Without a telescope, you would never see it. It shines at around magnitude 11, far below the threshold of naked eye visibility. For all practical purposes, standing in a dark field in the southern hemisphere and looking toward Centaurus, Proxima is invisible. What you see instead is A and B together. They appear as a single brilliant point to the unaided eye, the third brightest star in the entire night sky. Only Sirius and Canopus outshine them. For most of human history, anyone who looked up and noticed that bright point in Centaurus had no idea they were looking at two stars, let alone three. Not a single dot. A binary system, anchored by two stars that each rival our own sun. Alpha Centauri. A is a G-type star, the same spectral classification as the sun. This means it burns at a similar surface temperature, emits a similar color of light, and operates in the same broad regime of stellar physics. But A is not identical to our sun. It is roughly 10% more massive, about 23% larger in diameter, and approximately 50% more luminous. It is estimated to be between 5 and 6 billion years old, placing it in the same life chapter as our sun, mature but nowhere near the end. If you replaced our sun with Alpha Centauri A, the Earth would be warmer, but not uninhabitably so. The sky would look slightly different. The star would be a little brighter. The world would still be, in the broad sweep of the word, recognizable. Alpha Centauri B is somewhat smaller and cooler. It is a K-type star. One step down the spectral ladder from GB carries about 90% of the sun's mass, and emits roughly 50% of the sun's total light output. It burns a little more orange, a little more subdued, but it is still genuinely sun-like. Still a main sequence star in the prime of its life. Still the kind of star around which, in principle, the right conditions could exist. Together, A and B form the nearest binary system of sun-like stars anywhere in the galaxy. Two stars that our sun would recognize as kin, close enough that their gravitational relationship has lasted billions of years, different enough from each other that they present two distinct environments for anything orbiting them. For a century, astronomers treated this system as the most promising nearby address in the cosmos. Two near-solar twins at the edge of the reachable. The system most likely to harbor something familiar. The system we assumed we understood. The architecture alone was remarkable enough, but the architecture was only the beginning of what Alpha Centauri had to show us. Let's stay with that nearness for a moment. Not the geometry of it, not the orbital mechanics or the spectral classification, the feeling of it, the weight that has gathered around this system over more than 100 years of human imagination. Alpha Centauri became the default answer before most people had heard of exoplanets. Ask a scientist in 1950 where humanity should go first beyond the solar system. Ask a science fiction writer. Ask a physicist with a napkin and a dream. The answer, almost without exception, was the same. The nearest sun-like stars. The obvious choice. The only choice, really, if the word reachable was going to mean anything at all. The stories piled up. James Cameron placed Pandora, the moon from Avatar, in orbit around a gas giant in the Alpha Centauri system. Lost in Space, the television series from 1965, sent the Robinson family toward this same address. Liu Cixin, in The Three-Body Problem, gave the alien civilization that would threaten humanity a home in this system. The Civilization video game series made reaching Alpha Centauri the final achievement of human history. The last thing you build toward after everything else is done. Hundreds of millions of people absorbed these stories over decades. They did not all learn orbital mechanics, but they did absorb something. The implicit premise that Alpha Centauri was out there waiting. Familiar. Knowable. The kind of place that had a plot of land with our name on it. The scientists were not immune to this feeling. They built mission concepts around it. Project Daedalus was designed in the 1970s by the British Interplanetary Society. Its target was Barnard's star, slightly farther than Alpha Centauri, but the exercise proved the broader point. A two-stage fusion-powered spacecraft, in principle, could reach the nearest stellar neighborhood within a human lifetime. 50 years. Project Longshot followed in the late 1980s. Developed at the US Naval Academy. Its design called for a fusion probe that would take 100 years to arrive. Not fast by human standards, but conceptually serious. A real engineering proposal aimed at a real destination. Breakthrough Starshot went further. In 2016, Yuri Milner and Stephen Hawking announced a plan to send gram-scale laser-propelled spacecraft at 20% of the speed of light. At that speed, the transit would take roughly 20 years. Data would take another 4 years to return. A generation of waiting for images of another solar system. The concept still relies on technologies that do not yet exist at the necessary scale. But the ambition was genuine. And the destination, once again, was Alpha Centauri. Laser sails, antimatter drives, generation ships. Every road points the same direction. There is something specific about how this system feels, compared to the other bright nearby stars. Sirius is closer in terms of fame, the brightest star in Earth's night sky, but Sirius is a hot blue-white star, nothing like the Sun, alien in its character. Vega is beautiful and well-studied, but it sits 25 light-years away and carries a different quality. Remote. A reference point, not a destination. Alpha Centauri has always felt different from both. Almost domestic. The vacation home the family has been planning to visit for generations. The one that keeps getting postponed. The one everyone assumes is still there. Waiting. Exactly as imagined. That is what makes the actual data so striking. Here is what scientists believed heading into the modern era of exoplanet science. They believed Alpha Centauri was the most promising nearby target. They believed that sun-like stars in the nearest binary system almost certainly hosted planets. They believed that proximity would eventually translate into detection. But the reality was different. More than 6,000 exoplanets have now been confirmed across the galaxy. Worlds smaller than Earth around red dwarfs, hundreds of light-years away. Gas giants detected in the first years of the Kepler mission. Super-Earths orbiting dim stars, thousands of light-years from here. The tools have become so refined that we can detect a planet the size of Earth around a star we cannot even see with the naked eye from twice the distance of Alpha Centauri. And yet the nearest pair of sun-like stars in the galaxy has yielded exactly 0 confirmed planets. Not a handful. Not one. 0. Proxima Centauri is different. Proxima has 3 confirmed planets, including Proxima b, which sits in the habitable zone, the region where liquid water could theoretically exist on a surface. That sounds encouraging until you remember what kind of star Proxima is. A red dwarf. A violent one. Red dwarfs emit powerful flares of ultraviolet radiation and charged particles, outbursts that could strip a planet's atmosphere in geological blinks of an eye. Proxima b and its companions orbit so close to their star that they are almost certainly bathed in radiation levels hostile to life as we understand it. The question that matters most has never been about Proxima. It has been about A and B, the sun-like stars, the ones we recognize. And on that question, the record is empty. In 2012, that appeared to change. A European team of astronomers announced a detection using radial velocity, the method that measures tiny gravitational wobbles in a star caused by an orbiting planet. The planet was called Alpha Centauri BB, Earth mass, orbiting Alpha Centauri b with a period of 3.24 days, closer to its star than Mercury is to our Sun. The headlines were immediate. They were large. For a brief period, it seemed the long wait was over. It was not over. Subsequent independent analysis showed the signal was almost certainly not real. The radial velocity method works by detecting the subtle back and forth motion a planet induces in its host star. But in a binary system, both stars pull on each other gravitationally and introduce their own competing signals into the data. Separating the planetary wobble from the binary contamination is extraordinarily difficult. The researchers had done their best, but the artifact survived the processing. Alpha Centauri BB became one of the most famous false positives in the history of exoplanet science. The planet that wasn't. The Hubble Space Telescope observed the system directly. Ground-based adaptive optics, instruments that correct for atmospheric blurring in real time, targeted it. Transit searches, which look for the slight dimming of a star as a planet crosses its face, came up empty. Every method, every campaign, the same result. The nearest sun-like stars in the cosmos, the ones that have anchored a century of human dreaming about where we belong in the universe, have not yet shown us a single confirmed world. The cultural narrative is overdrawn. The data is silent, but there was still one more instrument left to point at this system. One more attempt. And what it returned was not silence. It was something harder to interpret. So why has the silence held? The answer is not what you would expect. It is not that the system is too far away. It is almost the opposite. Alpha Centauri is too close, too bright, too complicated, and that combination has turned our greatest astronomical advantage into a fundamental problem. Think about what it means for a star to be the third brightest object in the night sky. Alpha Centauri A is not merely visible, it is blazing. It pours light into every telescope pointed at it, flooding sensitive instruments designed to detect faint, quiet signals buried in near darkness. The detectors built to find planets were engineered for subtlety. Alpha Centauri A is not subtle. It is one of the loudest light sources in the southern sky, and that loudness overwhelms the very tools we would use to find worlds beside it. The picture did not hold. In astronomy, the usual enemy is distance. A star at 500 light-years is harder to study than one at 50. A star at 5,000 light-years is harder still. Faintness is the standard problem. You build bigger mirrors. You add more sensitivity. You collect more photons over longer exposures. Distance degrades your signal, and the solution is always more light-gathering power. But Alpha Centauri inverts that logic completely. A sun-like star at roughly 100 light-years is dim enough that planetary signals can actually be extracted from the data. The star itself recedes into the background, and a planet's influence becomes detectable by comparison. Move that same star closer, make it brighter, and the situation gets worse, not better. The noise floor does not drop. It rises. The signal you're trying to find stays the same size, and the overwhelming background grows around it. Proximity, which should make the system the easiest target in the sky, makes it among the hardest. Not the easiest system to study, one of the hardest. And it does not stop with one star. Alpha Centauri B is there too, orbiting A across a range of angular separations that shifts as the two stars move through their nearly 80-year orbit. From Earth, that separation varies between roughly 4 and 22 arcseconds, depending on where the two stars are in their cycle. 22 arcseconds sounds like a large gap. It is not. 22 arcseconds is approximately the apparent width of a small coin held at a quarter-mile away. That is the widest the two stars ever appear from our vantage point. At their closest, the gap shrinks to 4 arcseconds. Their light begins to blend. The glare from one contaminates the measurement of the other. Two blindingly bright sources separated by a distance that, on the sky, is essentially nothing. Think about what that means for a telescope trying to detect something faint orbiting either of them. Imagine a candle taped to the side of a lighthouse. The candle is real, it is burning, but you cannot see it. Not because it is too small or too far away, but because the lighthouse is pouring out so much light that the candle's glow is simply lost inside the flood. You cannot isolate it. You cannot measure it. The lighthouse is not hiding the candle on purpose. It is just doing what it does. Shining. Now put a second lighthouse beside the first one, a few inches away from your perspective. Both of them blazing. Both of them washing light across the same patch of sky. And now ask yourself to find the firefly hovering 6 inches from the nearer lighthouse. The firefly is there. It is glowing, but your camera cannot separate its faint light from the overwhelming brilliance right beside it. Every image comes back the same. Pure glare. The firefly is invisible, not because it does not exist, but because nothing in your instrument can pull it out of that environment. That is Alpha Centauri A and B as a planetary detection system. 2 lighthouses, 1 firefly, and no camera yet built that can reliably find it. The problem takes a specific shape for each detection method, and each shape is its own kind of wall. Radial velocity detects planets by measuring the gravitational wobble a planet induces in its star. As a planet orbits, it tugs the star forward and backward very slightly, and that motion shows up as a tiny shift in the star's spectral lines. It is a delicate measurement, sensitive to motions of a few meters per second in a star millions of kilometers across. In the Alpha Centauri system, A and B are pulling on each other constantly. That gravitational interaction produces its own enormous signal in the radial velocity data, a signal that dwarfs the wobble any planet could create. Separating a planetary signature from the binary's gravitational noise is not straightforward. It requires modeling the binary's influence, subtracting it, and then looking for whatever remains at the level of a few meters per second. The 2012 false positive was not incompetence. It was exactly this problem collapsing into a single surviving artifact. Transit photometry searches for the moment when a planet crosses the face of a star and blocks a small fraction of its light. The dimming is real, but it is tiny. For an Earth-sized planet crossing a Sun-like star, you are looking for a brightness drop of about 1 part in 10,000. Now add Alpha Centauri b's light to the measurement. The combined brightness of the system is higher than either star alone, and a higher baseline makes the relative depth of any transit signal smaller. The signal you are searching for shrinks as a fraction of the total brightness, dropping below the level where instruments can reliably distinguish planet from noise. Direct imaging tries to take a picture of the planet itself. It is the most intuitive approach and the most brutally difficult. Stellar glare does not simply add brightness to the frame. It generates structure, diffraction patterns from the telescope's optics, rings of scattered light, speckles and artifacts that move and shift as the instrument conditions change. Some of those artifacts look exactly like faint point sources. They look, in other words, exactly like planets. Distinguishing a real planet from an instrumental ghost requires extraordinary precision, and extraordinary precision is extremely hard to achieve when the source of the contamination is one of the brightest stars in the sky. 2 of them. The stars are screaming so loudly that we cannot hear anything else. That is the intuition. It is not a metaphor about indifference. It is a statement about physics. The signal is not absent. What we are trying to detect is probably there, statistically speaking, given what we know about how common planets are around Sun-like stars. But the instrument cannot reach below the noise. The noise is too high. And the noise is high because the stars are close. The same proximity that makes Alpha Centauri feel reachable, the same closeness that has made it the anchor of a century of human dreaming, is the exact quality that has made it so difficult to interrogate. Distance is astronomy's usual enemy. Here, closeness is. But the wall was not going to hold forever. Every limitation in observational astronomy is a temporary one. What cannot be seen today can sometimes be seen tomorrow, if someone builds the right instrument and points it carefully enough. And someone did. That instrument was Webb. And what Webb brought to the problem was not simply more power. It was a different way of seeing entirely. Every observatory that had tried before was fighting the same physics. In visible light, a sun-like star outshines a nearby planet by something close to 1 billion to 1. Not 1 million to 1. 1 billion. The star dominates so completely that the planet's contribution to the total light is essentially nothing. It is not a matter of sensitivity or resolution. It is a matter of contrast. When one source is 1 billion times brighter than another, the brighter one does not merely overshadow the fainter one. It erases it. But here is where the physics offers a narrow opening. Visible light is not the only kind of light. Warm objects glow. A gas giant, even a cold one by stellar standards, still radiates heat. That heat comes out not as visible light, but as infrared radiation, at wavelengths the human eye cannot see. And in the mid-infrared, the contrast ratio between a star and a warm planet drops dramatically. Not to nothing, but to thousands to 1 instead of billions to 1. The planet still glows. The star's relative dominance shrinks. For the first time, the gap between them becomes something an instrument might actually bridge. This is the logic behind Webb's MIRI instrument. MIRI stands for Mid-Infrared Instrument, and it was designed to observe exactly this regime. Think about it this way. Imagine you are standing in a dark room, trying to see a dim candle placed next to an ordinary light bulb. The bulb overwhelms everything near it. Now imagine the room changes. Now you're wearing heat-sensitive goggles, that respond to warmth rather than brightness. The candle's warmth still registers, but the bulb, which was blinding invisible light, produces a gentler signature in thermal terms. The gap between them narrows. The candle becomes findable. MIRI operates from something no ground-based telescope can replicate: the stable cold of deep space, far from Earth's vibrating atmosphere and its own infrared glow. Atmospheric turbulence blurs images. Earth's own heat contaminates infrared observations. Webb sits beyond both of those problems, at a point in space where the environment is cold, still, and dark. That stability is not just a convenience, it is a prerequisite. Mid-infrared direct imaging of a planetary companion requires conditions ground-based telescopes cannot maintain. But mid-infrared sensitivity alone was not enough. Even with the contrast advantage, the star is still overwhelmingly bright compared to anything planetary nearby. What MIRI also carries is a coronagraph. A coronagraph is a physical mask placed directly inside the instrument, positioned precisely over the star's image as it forms inside the telescope. It creates an artificial eclipse. The star's light is blocked at the source before it can flood the detector and wash out everything around it. What remains, in principle, is the faint region just around the star where a planet might be glowing quietly in the infrared. Coronagraphs are not new. They exist on other telescopes, including some on the ground, but those instruments fight the atmosphere with every exposure. MIRI's coronagraph operates in mid-infrared, from deep space, in conditions of extraordinary stability. That combination had never been applied to Alpha Centauri before. Webb was not simply another attempt with the same tools, it was a genuinely different class of observation. And yet, even with MIRI and the coronagraph, the Alpha Centauri problem pushed everything to its limits. The stars are bright. They are among the brightest sources Webb can observe, and the standard way Webb acquires its targets does not work for Alpha Centauri A. The star is simply too bright. The normal target acquisition procedure would saturate the detector before useful data could be collected. That alone required a custom solution. Then there is motion. Alpha Centauri is close. It moves across the sky faster than most targets Webb was built to observe. Any observing sequence would have to track it precisely across the duration of the exposure. Standard procedures do not account for that kind of motion at that kind of brightness simultaneously. Then there is the binary problem. Even if the coronagraph perfectly blocks Alpha Centauri A, Alpha Centauri B is still there, blazing at a separation of a few arcseconds. No single coronagraphic mask can cover two sources at once. Block A and B remains. B's light spills across the field. It scatters. It contaminates. The second star becomes the second wall. The team at the Space Telescope Science Institute, the organization that manages Webb's operations and science program, had to build an entirely custom observing sequence for this target from scratch. The standard toolkit was not adequate. This was not a routine pointing of a great telescope at an interesting target. It was a bespoke engineering solution assembled specifically for a system that broke the assumptions behind the normal approach. All of that difficulty came with a motivation that justified every piece of it. If this observation worked, the scientific payoff would be unlike anything achievable anywhere else. A confirmed planet around Alpha Centauri A or B would be the closest directly imaged exoplanet ever found. Not one of the closer ones. The closest, by far. Around the nearest pair of sun-like stars in the sky, at a distance so small that the planet would be accessible for follow-up in ways no other known exoplanet could match. Atmosphere characterization, temperature mapping, long-term monitoring of how the planet changes across its orbit. None of that is possible for planets around stars hundreds of light years away. Here, the distance itself becomes the advantage. The same proximity that had made the system so difficult to interrogate could, once breached, make it the most studied planet outside our own solar system. The effort was worth the difficulty. The question was whether the difficulty could actually be solved. And the answer began with a technique that had no name until the people who needed it invented one. That technique had a name now, and it was time to use it. Alpha Centauri A sat behind the coronagraphic mask. MIRI was collecting light. Not visible light, the kind your eye registers as a star's bright point in the sky, but mid-infrared light at a wavelength of 15.5 microns. To anchor that number, 15.5 microns sits in the thermal infrared region of the spectrum. This is the wavelength range where room temperature objects glow. Hold your hand in front of an infrared camera, and your skin radiates in this regime. A gas giant planet warmed to a few hundred degrees radiates here too. Strongly. Far more strongly than it ever would in visible light. And a star like Alpha Centauri A, while still dramatically brighter, no longer dominates by billions. At this wavelength, the contrast between star and warm giant planet shrinks to thousands. Not billions. Thousands. The gap narrows enough that, in principle, something hiding in the shadow might be found. In principle. The coronagraph had done its part. It had positioned its mask over the bright core of Alpha Centauri A, creating something like an artificial eclipse inside the instrument itself, cutting off the star's direct light before it could flood the detector. That was the tool. That was what made mid-infrared observation at this distance even conceivable. And if the universe cooperated cleanly, the image beyond the mask would show a darkened field where faint sources could emerge. But here is where it gets strange. The coronagraph blocks the star, except it does not. Not really, not cleanly. What the detector actually receives is not a neat dark circle surrounded by open sky. It receives the star's light, still arriving, scattered and bent into complex patterns that spread across the image in all directions. Light bends around the mask's physical edges. That bending, a property of light itself called diffraction, generates rippling patterns that spread outward from the mask, like waves moving across the surface of a pond after a stone breaks the water. The waves are faint, but they are present, and they are structured, and they are bright enough to matter. The telescope itself adds more. Webb's primary mirror, its support struts, its internal baffles, all of the physical architecture that makes the instrument work, each of those surfaces catches starlight and scatters it. That scattered light produces circular rings around the masked star. It produces spoke-like features extending outward. It fills the image with a texture of faint artifacts that has nothing to do with the actual sky and everything to do with the instrument looking at it. Now look at what the detector is holding. Rings of light at various radii from the masked star. Spots brightening along those rings. Spokes of scattered light cutting across the field. A faint, complex layered glow where there should be darkness. And somewhere in that glow, if a planet exists, its signal is buried. It would appear as a faint point of light, a small bright spot in the image. The problem is that the diffraction rings and scattering patterns also produce small bright spots. Every ring has brighter and dimmer regions. Every scattered feature has structure. The image after coronagraphic masking is a minefield of optical illusions. A bright spot in a diffraction ring looks exactly like a planet. A peak in a scattered light feature looks exactly like a planet. The instrument designed to help find one thing has created a field full of false candidates. This was the first obstacle waiting on the other side of the mask. The second was already there, blazing. Alpha Centauri B had not gone anywhere. The coronagraph blocked one star, not both. Alpha Centauri A was behind the mask, its core suppressed, but B sat at its own position in the field, separated from A by a few arc seconds, and B is not a dim companion. It is a K-type star, slightly smaller and cooler than the Sun, but still a star, still pouring out light at a scale that dwarfs any planetary signal by a vast margin. B's light was landing on the detector without any coronagraphic blocking at all. It was generating its own diffraction patterns, its own rings, its own scattered light features, its own minefield, and those features were spreading outward from B's position, overlapping with the residuals already spreading from behind A's mask. The two sets of artifacts were layered on top of each other in the same image. This was the environment the team was working in. Not a cleaned image with a few faint signals to examine. A dense, overlapping field of optical artifacts from two bright stars, contaminating every region of the detector at once. The only path through it was subtraction. layer by layer. The process worked in stages. First, the team observed reference stars. These were other stars, not Alpha Centauri, selected because their brightness and spectral properties matched Alpha Centauri A closely. A star with the same brightness produces roughly the same coronagraphic artifacts when placed behind the same mask. So observing those reference stars with the same instrument in the same configuration gave the team a model of what coronagraphic residuals look like for a star of A's type. A map of the instrument's fingerprint, built from stars that had no planetary companions to protect or reveal. That model was then subtracted from the Alpha Centauri data. Take the raw image, remove the modeled artifact pattern. What remains is the residual after the instrument's own contribution is peeled away. The image has not become clean, but one layer of contamination is gone. Then came the second subtraction. Alpha Centauri B's contribution had to be removed computationally. There was no mask to block it, so the team used algorithms, mathematical models of how B's light scattered and diffracted across the detector to build a representation of B's optical fingerprint in the image. That fingerprint was then subtracted from the data, effectively erasing the second star not from the sky, but from the measurement. Think about what this means. Two bright stars. The first one masked, but still leaking complex patterns. The second one unmasked, blazing freely. A detector covered with the overlapping fingerprints of both. And the task is to remove each fingerprint, one at a time, without accidentally removing any real signal hiding beneath. The analogy that fits is peeling an onion. Each subtraction removes a layer of contamination. The outer layer, the coronagraphic residuals from A, modeled from reference stars and removed. The next layer, the scattered light and diffraction from B, modeled computationally and removed. Each layer comes off and reveals another layer beneath, and only after the last layer is gone does the underlying data become readable. Real seeing had not begun at the moment the mask closed over Alpha Centauri A. Real seeing only began after the data had been processed, peeled, stripped of artifact. The coronagraph was not the tool that found the answer. It was the tool that made the subsequent work possible. What the subtracted image would ultimately contain was still unknown. The peeling could reveal a real source, a faint point of thermal infrared light sitting at a position where no diffraction ring or scattered artifact should be. A signal that persisted through the cleaning rather than disappearing with it. Or it could reveal nothing. A field of uniform residual noise, consistent with an empty sky. The layers had been removed. The answer was in what remained. And what remained would reshape everything that came before it. Before that image had fully settled, something shifted. The question of what remained in the data had an answer, but to understand that answer, it helps to go back one step further, to the moment before any data existed at all, to the moment Webb first tried to look. Pointing a space telescope is usually straightforward. The guidance system locks onto a target star, confirms alignment, centers it, and the observation begins. Webb has done this thousands of times since it began science operations in 2022. For most targets, it is the least interesting part of the process. A surgeon washing their hands before an operation. Essential, but rarely the part anyone worries about. For Alpha Centauri A, even pointing was a problem. Webb's guidance sensors are built for stars of manageable brightness. They are calibrated for the faint and the distant, for the ordinary stars that populate the sky. Alpha Centauri, A is not ordinary. It is the fourth brightest star system in the sky, blazing from a distance of only 4.3 light-years. Point Webb's guidance sensors directly at it and the sensors saturate instantly. Not dim and recoverable, blind and useless. The star overwhelms the very instruments needed to aim the telescope, so the team could not simply point at what they wanted to see. The solution was a technique called a blind offset. Instead of locking onto Alpha Centauri A, the operations team locked onto a different star entirely. That star was Epsilon Muscae, a red giant sitting roughly 330 light-years away in the constellation Musca. At that distance, its light is manageable, its brightness far below the saturation threshold. Webb's guidance system locked onto it without difficulty. And then, from that position, the telescope slewed, rotating by a precisely calculated angular distance, placing its field of view exactly where Alpha Centauri A should be, dropping the star behind the coronagraphic mask without ever seeing it directly. Think about what that required. The team was not pointing at a target. They were pointing at the memory of where a target should be, calculated in advance, trusted completely. If the calculation was off by even a fraction of an arc second, the star would land beside the mask instead of behind it. Starlight would pour around the edges. The contamination would be catastrophic. The whole observation would be lost before a single photon of science had been collected. It is something like parking a car in a specific spot while blindfolded, using only the knowledge that the space is exactly 47 steps to the left of a lamppost you touched 3 minutes ago. One step short or long and you were in the wrong lane entirely. The operations team succeeded. The star landed behind the mask. The custom sequence worked. And only after that preparatory act, that act of extraordinary precision that no standard procedure covered, did the real observation begin. What emerged from the August 2024 data, after all the processing and subtraction, was a faint point source. A single spot of light at a projected separation of roughly 2 astronomical units from Alpha Centauri A. The team designated it S1. The brightness of S1 relative to Alpha Centauri A at the observation wavelength of 15.5 microns was more than 10,000 times dimmer than the star itself. Think about the scale of that. If Alpha Centauri A were a concert arena packed with 10,000 screaming fans, S1 would be a single person whispering in the back row. Not shouting, whispering. That was the signal the team was trying to isolate. That was what survived the peeling. But detecting a faint point source is not the same as discovering a planet. Exoplanet science has seen this before. Faint blobs in processed astronomical images have a history of turning out to be artifacts, background galaxies, foreground objects, processing errors. The field is littered with candidates that evaporated under scrutiny. S1 had to be tested. The first question was whether S1 could be a background star or galaxy, something sitting far behind Alpha Centauri and coincidentally appearing in the field. Here, the system's proximity worked in the team's favor. Alpha Centauri moves across the sky rapidly, a consequence of how close it is. Background objects appear to shift in the opposite direction as the star moves. Archival images of that region of sky showed no known background source at the position S1 occupied. That explanation became unlikely. The second question was whether S1 could be a foreground solar system object, an asteroid drifting through the field during the observation. The geometry did not support it. The brightness was inconsistent with a nearby rocky body at that distance. That explanation also became unlikely. The third question was the hardest. Could S1 be an instrumental artifact, a ghost image produced by the telescope itself? This is normally where a technique called angular differential imaging resolves the question. The telescope rolls between exposures. Real objects in the sky rotate with that roll, moving in a predictable arc. Instrumental artifacts stay fixed, locked to the telescope's geometry. Separate them, and you know which category your candidate falls into. Something else was happening. In the August 2024 observation, sequence complications prevented the roll maneuvers from being cleanly applied. The standard test could not be completed in the standard way. S1 existed in a dataset that was missing the clearest instrument to distinguish real from false. The team did not stop there. They ran S1 through extensive alternative analyses. They compared its spatial properties against the known signatures of instrumental artifacts, testing whether its position, brightness, and shape were consistent with any ghost pattern the system was known to produce. They ran statistical tests to quantify the probability of a false detection. They examined the data for internal consistency. S1 did not behave like an artifact. It did not match the known patterns. The statistical test did not condemn it. The conclusion was careful. S1 was unlikely to be an artifact, unlikely to be a background or foreground source, most probably a real astrophysical object associated with Alpha Centauri A, not a confirmed planet. A candidate, unlikely to be false, is not the same as certain to be real. The team was precise about what the evidence could and could not say. But if S1 is real, then the question of what it is becomes one of the most significant questions in the history of exoplanet science. Based on its brightness at 15.5 microns and its projected separation, S1 is most consistent with a gas giant comparable in mass to Saturn. Not a rocky world. Not Earth-like. A planet without a solid surface, made of gas, incapable of supporting life as we know it. Its orbit appears to range between roughly 1 and 2 astronomical units from Alpha Centauri A, tracing an elliptical path through the star's habitable zone, the region where liquid water could exist on a rocky surface, though S1 itself has no such surface. Its orbital period is estimated between roughly 1.5 and 3 Earth years. Its orbit is steeply inclined relative to the plane of the binary system, tilted by somewhere between 50 and 130 degrees. It is a world in a canted, eccentric path around the nearest sun-like star. That location is remarkable regardless of what S1 is made of. To understand what S1 would mean for exoplanet science, it helps to remember where the field stands. The first planet confirmed around a sun-like star was 51 Pegasi b, detected in 1995 by Michel Mayor and Didier Queloz using the radial velocity method, the technique that measures the gravitational wobble a planet induces in its host star. Since then, roughly 6,000 exoplanets have been confirmed across the galaxy. The vast majority were never seen directly. They were inferred. A dimming of light as something crossed in front of the star. A wobble in the star's spectrum as something pulled it from one side. The planet itself remained invisible. A shadow, a tremor. Direct imaging is different. In direct imaging, you capture a separate point of light from the planet itself. Not a wobble, not a dimming. A photograph. It sounds simpler. It is far harder. Of all the thousands of exoplanets confirmed, only a handful have been directly imaged, and almost every one of them follows the same pattern. They are young planets, still radiating the heat of formation, temperatures over 1,000 degrees. They are massive planets, several times the mass of Jupiter, and they orbit far from their stars, tens to hundreds of astronomical units out, where the contrast ratio is less brutal because the star's scattered light has spread and faded. S1 fits none of those categories. Its temperature regime is estimated at a few hundred degrees, not over 1,000. Its mass is comparable to Saturn, not multiple Jupiters. Its orbit is 1 to 2 astronomical units from its star, not tens or hundreds. And its star sits 4 light years from Earth, not dozens or hundreds of light years away. Not incremental progress. 4 simultaneous records. The coldest directly imaged exoplanet ever found. The lowest mass directly imaged exoplanet ever found. The closest to its host star of any directly imaged exoplanet ever found. And the nearest to Earth of any directly imaged exoplanet ever found. Any one of those records on its own would be a notable result. The kind of thing that earns a paper and a place in the textbooks. Push direct imaging to a colder planet than ever before, and you have extended the method into a new temperature regime. Push it to a lower mass, and you have shown it can find smaller worlds. Each record is a frontier moved. What makes S1 extraordinary is that it would move all 4 frontiers at once, with a single detection in a single system. Not a careful step past one limit while staying comfortably inside the others. A leap past all of them simultaneously, into territory the method was never thought capable of reaching. And the reason all 4 cluster together is not coincidence. They are the same achievement seen from 4 angles. A planet that is cold, low in mass, close to its star, and near to Earth is precisely the kind of planet that direct imaging was supposed to be unable to find. Because every one of those properties makes the contrast problem harder. Cold means faint. Low mass means faint. Close to the star means buried in glare. The only property that helps is nearness to Earth. And even that is a double-edged gift. Because the nearest sun-like star is also the brightest and most overwhelming. S1 would be a detection assembled entirely out of disadvantages, every factor stacked against it, and found anyway. Every previous direct image reached outward for the easiest targets, the brightest, the hottest, the most distant from their stars. S1 would mean that direct imaging can now reach inward, into the temperate, lower mass regime where the planets that matter for understanding whether life might exist are actually found. That would not be an expansion of the catalogue. It would be an expansion of what the catalogue can contain, and S1 was a candidate, not a confirmation. The next observation was the only thing that could close that gap. So the team looked again. Director's discretionary time is the mechanism major observatories use for urgent science that cannot wait for the normal proposal cycle. When something unexpected appears in the data, a small committee can authorize follow-up observations quickly, sometimes within weeks. The Webb team used that mechanism. They secured time on the same instrument, the same coronagraphic configuration, the same processing pipeline that had produced the August 2024 result. Understand what that decision costs. Webb is the most contested telescope in the history of astronomy. For every hour of observing time awarded, several hours worth of proposals are turned away. Cosmologists studying the first galaxies, planetary scientists mapping the atmospheres of distant worlds, teams who have waited years for their turn, all of them competing for the same finite resource. To pull time out of that queue on short notice, a result has to be compelling enough that a committee is willing to displace other science to chase it. S1 cleared that bar. That alone tells you how seriously the team took what they had found. They were not idly curious. They believed there was something there worth interrupting the schedule for. And they wanted to repeat the conditions exactly, not improve them, not refine them, repeat them. The logic was simple. If the original detection was an artifact of a particular instrument configuration, then reproducing that configuration and finding nothing would expose the artifact for what it was. If the detection was real, then reproducing the configuration should, in principle, recover the signal. The follow-up was designed as a clean test. Same mask, same wavelength, same subtraction, change as little as possible, and let the sky give its answer. In February 2025, they pointed Webb at Alpha Centauri A. They ran the observation, they processed the data. S1 was gone. They looked again in April 2025. Same instrument, same approach, same careful subtraction of Alpha Centauri A's glare, the same removal of B's contaminating light. S1 was gone again. The team verified the data thoroughly. The February and April observations were clean. The processing had worked. The instrument had functioned correctly. There was nothing wrong with the follow-up observations. S1 simply was not there. Aniket Sanghi, a PhD student at Caltech and one of the co-first authors on the discovery papers, described it plainly. "We are faced," he said, "with the case of a disappearing planet. The naive interpretation was hard to avoid. A single detection followed by two non-detections normally points in one direction. The original signal was probably spurious, an artifact that survived one round of processing but not the next two. A statistical fluctuation that looked like a source and then revealed itself as noise. The system had already delivered one famous false positive in 2012. This would be the second. But before closing the case, the team turned to orbital mechanics. A real planet on an elliptical orbit does not stay still relative to the coronagraph. It moves. At some points in its orbit, it swings far enough from the star that its projected distance from the stellar core exceeds the coronagraph's blind zone, and it appears in the detector field as a faint point source. At other points, it swings inward, its apparent position in the sky falling within the region of residual glare the coronagraph cannot suppress. At that point, it vanishes. Not because it stopped existing, because the instrument cannot reach it. There is a specific geometric limit at work here. The coronagraph has what astronomers call an inner working angle, which is the minimum projected separation between the star and a source at which the instrument can still suppress the glare enough to detect something. At 15.5 microns through Webb's MIRI coronagraph, that inner working angle corresponds to roughly 0.5 astronomical units at Alpha Centauri's distance. Any source whose apparent separation from the star falls below that threshold becomes invisible, swallowed by residual light the mask cannot remove. The subtlety is geometric. A planet does not need to be physically close to the star to fall inside that threshold. It needs only to appear close from Earth's perspective. A planet on a tilted, eccentric orbit can be physically 1.5 AU from its star, while its projected separation as seen from Earth is only 0.3 AU. From the instrument's point of view, that planet is behind the glare wall. It is there. It is simply unreachable. This is the kind of distinction that is easy to state and hard to feel, so it is worth slowing down on. When we look at a distant solar system, we are not seeing it from above, laid out flat like a diagram in a textbook. We are seeing it edge on, or nearly so, or at some random angle determined by how the system happens to be tilted, relative to our line of sight. A planet tracing a wide circle around its star, viewed from the side, does not appear to move in a circle at all. It appears to slide back and forth along a line, swinging out to one side of the star, then crossing back through, then swinging out to the other side. At the extremes of that swing, the planet looks far from the star. At the midpoint, when it passes in front of or behind the star from our vantage, it looks as though it is sitting almost on top of it, even though in physical space it may be more distant from the star than it ever is at the visible extremes. That projection effect is what governs whether a coronagraph can see a planet at any given moment. The instrument does not care how far the planet actually is from its star. It cares only about the apparent gap between the 2 points of light on the detector. Shrink that apparent gap below the inner working angle, and the planet drops into the unrecoverable zone, regardless of where it physically sits. A world can be comfortably outside the glare in real space and completely buried in projected space at the same instant. Earth's viewing angle, fixed and unchosen, decides which. So when S1 vanished, there were two stories the data could be telling. In the first, there had never been a planet, and the original signal was noise that happened to survive one round of processing. In the second, there was a planet and it had simply swung into the projected zone the coronagraph cannot penetrate, hiding in plain sight behind a wall of residual starlight. The two stories produce identical observations. A blank field in February, a blank field in April. From the images alone, you cannot tell them apart. The team ran millions of simulated orbits. They start from the August 2024 detection, one known position, one known brightness, a set of physical plausibility constraints. From a single snapshot, you know where the planet was once. You do not know its speed, the shape of its orbit, or how it is oriented in space. Millions of different orbits could pass through that same point at that same moment. So the team generated them all, varying eccentricity, inclination, the orientation of the orbital ellipse in 3 dimensions, and the orbital period, drawing values from distributions consistent with what physics allows in a binary system. Picture the problem this way. You are handed a single photograph of a ball, frozen in midair. From that one frame, you can see exactly where the ball is. You cannot see where it is going. It could be rising or falling. It could be moving fast or slow. It could be on a steep arc or a shallow one. 1,000 different throws could put a ball in precisely that spot, at precisely that instant. With one frame, you cannot choose between them. You can only enumerate the possibilities and ask which ones are consistent with everything else. You know, the height of the room, the laws of motion, the fact that the ball did not pass through a wall to get there. That is what the team did with S1, except the ball was a planet and the room was a binary star system with its own gravitational rules. Each simulated orbit was a candidate throw. Each one placed the planet at the August 2024 position with a different velocity, a different tilt, a different shape of path. And each one made a prediction about where the planet would be at every other moment, including the 2 follow-up windows in February and April 2025. For each simulated orbit, they asked a binary question. Would the planet have been visible during the February 2025 window? Would it have been visible during the April 2025 window? The result was striking. In 52% of the stable simulated orbits, the planet would have been inside the inner working angle during both follow-up windows, invisible to Webb in February, invisible in April, not absent from the system, hidden by geometry. But the orbital modeling added another layer. Not all orbits that pass through the August 2024 position are physically stable over long timescales. Alpha Centauri B's gravity is always present. Orbits that stray too far from A cross into B's gravitational reach and get scattered out of the system over millions of years. Other orbits, depending on their inclination relative to the binary plane, become subject to a gravitational feedback mechanism called Kozai-Leadov oscillations. Think of a top that wobbles at first gradually and then increasingly wildly until it topples. Kozai-Leadov oscillations do something similar to orbital inclinations in binary systems. B's gravity periodically pumps the planet's orbital eccentricity higher and higher over long timescales, eventually driving it into the star or ejecting it entirely. Any orbit susceptible to that process would not have survived for billions of years. The simulations filtered those out. After applying dynamical stability constraints, the surviving orbits clustered around specific parameter ranges, orbital periods between 1.5 and 3 years. Eccentricities centered around 0.4, which means the orbit is noticeably elongated, not circular. Inclinations significantly tilted relative to the binary plane between roughly 50 and 130 degrees. These numbers are not arbitrary choices. They are the solutions that simultaneously explain where the planet was seen in August 2024, where it was not seen in February and April 2025, and how it could have survived in a gravitationally complex binary system long enough for anyone to be looking at it now. Here is where the reasoning inverts in an important way. The two non-detections were not evidence against the planet. They were positive constraints. Each non-detection carved away a family of orbits. Any orbit that would have placed the planet in a visible location during February or April was eliminated. What remained were orbits consistent with the planet genuinely being present but hidden. The absence of a detection became data. This is a strange thing to sit with, because it runs against the grain of how we normally treat absence. In everyday reasoning, not finding something is weak evidence at best. You look in the drawer, the keys are not there, and you conclude very little. Maybe they are somewhere else, maybe you missed them. But in a system governed by orbital mechanics, absence is not vague, it is sharp. A planet on a given orbit must be at a specific place at a specific time. If that place was inside Webb's reach during the follow-up windows, and Webb saw nothing, then that orbit is wrong. Not unlikely. Wrong. It is ruled out with the same confidence that a detection would rule it in. So the two empty images were not failures. They were measurements. Each one was a question put to the full population of possible orbits, and the population that survived both questions was smaller, tighter, more specific than the population that existed before the follow-ups were taken. The team had started with millions of candidate paths and used 2 blank fields to prune them down to a coherent family. The planet, if it existed, was no longer free to be anywhere. It had been boxed into a narrow corridor of orbits that fit every piece of evidence at once. And then, a different piece of data resurfaced. In 2019, a team led by Kevin Wagner at the University of Arizona's Steward Observatory used an instrument called NEAR to observe Alpha Centauri A. NEAR stands for Near Earths in the Alpha Centauri region, a thermal infrared coronagraph specifically built to search for planets in the habitable zones of Alpha Centauri A and B. It was developed through a collaboration between the European Southern Observatory and Breakthrough Watch, the observational program within the Breakthrough Initiatives. NEAR was installed on the Very Large Telescope's Unit Telescope 4 in Chile, and was purpose-built for exactly this search. Wagner's team observed for approximately 100 hours across several weeks. That is a significant investment of time on one of the most heavily scheduled observatories in the world. A faint source emerged near Alpha Centauri A at a projected separation of roughly 1.1 astronomical units. The team designated it Source C. Source C was intriguing and inconclusive in equal measure. The observation arc spanned only a few weeks, which was not long enough to determine whether the source was moving consistently with an orbiting planet, or whether it was stationary, as a background artifact or a dust structure would be. It could have been a genuine planet. It could have been a clump of warm dust in the disk surrounding the star. It could have been an instrumental ghost, a faint echo of Alpha Centauri A's glare that survived the subtraction imperfectly. The team published their findings in 2021 in Nature Communications, framing Source C as a candidate requiring further investigation. Properties consistent with a Neptune to Saturn mass planet, but other explanations could not be ruled out. The scientific community received the result cautiously. Without independent confirmation, Source C sat in the literature for 4 years, occasionally cited at conferences, never confirmed, never definitively ruled out. Then Webb observed Alpha Centauri A in August 2024 and found S1. Different telescope, different instrument, different wavelength, different position relative to the star, but the same system, the same host star, a source in broadly the same mass regime. The coincidence was impossible to ignore. Could S1 and Source C be the same world, seen at different points in its orbit 5 years apart? If so, that would mean the planet had been leaving fingerprints in the data since 2019 without anyone connecting them. The team built orbital models incorporating all 4 data points together: the 2019 near detection, the August 2024 Webb detection, the February 2025 non-detection, and the April 2025 non-detection. 2 detections at different positions, 2 non-detections at specific windows. They tested whether a single coherent orbit could explain all 4 simultaneously. It could. The combined picture that emerged gave specific inferred properties: a mass between roughly 90 and 150 Earth masses, a radius close to that of Jupiter, an orbital period between 2 and 3 years, an eccentricity of approximately 0.4, a perihelion, the closest point to the star, of roughly 1 astronomical unit, and an aphelion, the farthest point, of roughly 2 astronomical units, 2 inconclusive detections, and 2 non-detections. None of the 4 data points constitutes a discovery on its own. Together, they sketch the outline of a world that appears and disappears on a schedule consistent with orbital motion. Suggestive, coherent, not proof. Charles Beechman, the executive director of the NASA Exoplanet Science Institute at Caltech and a co-lead author on the work, framed what confirmation would mean. If this planet is real, every subsequent observation becomes easier than for any other known exoplanet. Atmospheric measurements, orbital refinement, the search for moons, all of it made more tractable by the sheer closeness of the system. And the orbital models make a specific, testable prediction. If S1 and Source C are the same world on the favored orbit, Webb's coronagraph should see the planet again in August 2026. That prediction is either going to hold, or it is not. Either the planet reappears on schedule, and the case becomes very difficult to dismiss, or it fails to appear and the candidate dissolves. The outline is drawn. The test is scheduled. The answer is not yet in. But that suspended state, that outline drawn and test scheduled, assumes the question has only 2 possible answers: planet or not planet, real or artifact. The candidate exists or it does not. There is a third possibility, and it does not dissolve easily. To understand it, set S1 aside for a moment. Step back from the specific coordinates, the orbital simulations, the August 2026 prediction. Step back to the larger question underneath all of it. Not whether S1 is real, but how we would know. How anyone, using any tool we have, finds a planet at Alpha Centauri at all. The honest answer is that every method we have breaks here in its own particular way. Start with radial velocity. It is the workhorse of exoplanet science. The principle is straightforward. A planet's gravity does not just send the planet around the star, it also tugs the star in response, pulling it slightly toward and away from Earth as the planet orbits. That tiny back and forth motion shifts the wavelength of the star's light. When the star moves toward us, its light compresses toward the blue end of the spectrum. When it moves away, it stretches toward the red. Measure those shifts with a sensitive spectrograph, and the signature of an orbiting planet emerges in the data. That method works brilliantly for single stars. Alpha Centauri is not a single star. Alpha Centauri A and B orbit each other on an 80-year cycle. As they trace that orbit, each star swings toward and away from Earth with a gravitational pull thousands of times larger than any planet in the system could produce. That binary motion floods the radial velocity signal before any planet has a chance to register. Before you can search for planets, you have to model the binary's motion precisely and subtract it out. Then you search what remains. But any imperfection in that subtraction leaves behind residual noise. And residual noise can look exactly like a planet. That is precisely what happened in the 2012. A team led by Xavier Dumusc used the HARP spectrograph at ESO's La Silla Observatory in Chile. They had monitored Alpha Centauri b for years, building up a long and careful dataset. They reported a periodic signal consistent with an Earth-mass planet on a 3.24-day orbit. Newspapers declared the nearest Sun-like star had a world. Within 2 years, independent analyses dismantled the claim. The binary subtraction had introduced systematic errors. Combined with the cadence of when observations were taken, those errors had carved a ghost signal into the data. A pattern that looked like a planet, behaved like a planet in the numbers, and was not a planet. Not incompetence, not carelessness. The binary subtraction had just left enough residue in exactly the wrong place, and the telescope's rhythm had reinforced it. The episode left a mark on the field. It was a lesson in how a method can betray careful people. The Dumusc team had not cut corners. They had built one of the most meticulous radial velocity datasets ever assembled for any star, monitored over years, processed with the best tools available. And the answer they extracted was a phantom, a pattern stitched together from the residue of an imperfect subtraction and the uneven cadence of when the observations happened to fall. The signal passed every internal check the team could devise. It looked exactly like what a small planet should look like. It was simply not there. That is the danger that haunts every subsequent attempt at this system. It is not that the methods are crude. It is that the methods can produce confident, detailed, internally consistent answers that turn out to be artifacts of the analysis rather than features of the sky. Alpha Centauri does not just resist detection, it manufactures false detections, signals convincing enough to reach headlines and then dissolve under independent scrutiny. Every team that points an instrument at this system now works in the shadow of that 2012 result, knowing that the system has fooled good scientists before and is entirely capable of doing it again. Newer instruments have pushed deeper. Espresso, installed on the Very Large Telescope, improved radial velocity sensitivity significantly. Binary contamination remains. No radial velocity detection at Alpha Centauri A or B has survived independent confirmation. Transit photometry runs into a different wall entirely. The technique looks for the tiny brightness dip when a planet crosses in front of its star, blocking a fraction of the starlight. It powered Kepler and TESS to thousands of confirmed discoveries. At Alpha Centauri, a geometric problem takes over before the instrument even matters. The probability that a planet at roughly 1 astronomical unit around a sun-like star happens to orbit in exactly the right plane to transit as seen from Earth is around 0.5%. Roughly 1 in 200 such systems would show transits at all. You cannot change that geometry. You observe and hope the odds fell your way. Even if they did, the photometric precision required to see the dip is swamped by systematics at this brightness level. An Earth-sized planet crossing a sun-like star produces a brightness drop of around 0.01%. At Alpha Centauri's extreme brightness, tiny variations in detector response, atmospheric fluctuations, and instrumental drift produce fluctuations that bury that signal entirely. A proposed mission called Ptolemy has explored astrometric approaches to this problem and remains in development, but no transit has been detected. Then there is direct imaging. What Webb used? The method that produced S1. It bypasses the binary subtraction problem entirely. It bypasses the geometric transit lottery entirely. It looks for the planet directly, reading its thermal glow in the mid-infrared, but it trades those problems for a different set. And at Alpha Centauri, the set is severe. The contrast between a sun-like star and a gas giant in the mid-infrared runs to roughly 10,000 to 1. For a rocky Earth-sized world, it reaches about 1,000,000 to 1 in mid-infrared. In visible light, that same rocky world disappears behind a contrast ratio in the billions. The coronagraph suppresses the star's light, but no coronagraph is perfect. Tiny imperfections in the mask, in the mirror surface, in the alignment, allow light to leak through and bloom into the field of view. At Alpha Centauri's extreme brightness, that leaked light manufactures artifacts bright enough to mimic a faint point source. One compact bright spot in the image could be a planet. It could be a coronagraph imperfection, catching the light at the wrong angle. And Alpha Centauri does not give you one contaminating source, it gives you two. Blocking A leaves B blazing unmasked in the same field, generating its own independent family of diffraction rings and scattered light structures overlapping with A's residuals. The system doubles the interference before the observation even begins. Webb's team worked through all of it: blind offsets, reference star subtraction, computational modeling of B's contribution, multi-layer cleaning of the data. They produced a candidate. That achievement is real, but the candidate exists in a domain where something else can also produce a faint, compact, mid-infrared source at exactly the kind of separation S1 occupies. In our own solar system, fine particles from comet debris and asteroid collisions orbit the Sun in a diffuse disk concentrated near the plane of the solar system. That zodiacal dust glows in the infrared. On a clear, dark night away from city lights, its reflected light is faintly visible from Earth, as a soft cone rising from the horizon, after sunset or before dawn. Subtle, easy to miss, but real and measurable. Most Sun-like stars are expected to host an analog, an exozodiacal cloud, their own diffuse reservoir of warm dust emitting in the mid-infrared. If Alpha Centauri A has one, that dust could produce compact brightness features in a coronagraphic image, not spread evenly across the field, but clumped. A concentration of warm particles at the right distance from the star, in the right position in the orbit, could appear as a localized source in one observation. The Webb team addressed this directly. They used their data to place an upper limit on the density of exozodiacal dust around Alpha Centauri A, no more than a few hundred times the density of our own solar system's zodiacal cloud. That is itself a valuable scientific result, a constraint that did not exist before this observation, but it does not rule dust out. A moderately dense clump of warm dust sitting at the right position during the August 2024 observation could have produced a signal consistent with what was seen. A compact bright source at roughly 2 astronomical units. Then the clump dissipates, drifts, cools, or scatters. The next 2 observations find nothing. The pattern is identical to what was observed. Distinguishing a planet from a dust feature in mid-infrared coronagraphic data is genuinely difficult. Both emit thermal radiation at similar wavelengths. Both can appear as compact sources at similar separations from the host star. The data alone cannot separate them. Here is where the distinction ultimately lives. A planet follows the laws of orbital mechanics. It moves predictably. Its position at any future time can be calculated from its past position and velocity. It does not dissolve. It does not reform somewhere else. A dust clump obeys no such schedule. It can drift unpredictably. It can dissipate entirely in weeks. It can brighten in one epoch and vanish in the next without leaving a trace that follows any orbital model. This is the cruel symmetry of the dust hypothesis. Everything that made S1's disappearance explicable as a planet on an eccentric orbit also makes it explicable as a clump of warm dust that simply was not there anymore. A planet vanished because geometry hid it. A dust feature vanished because it stopped existing. Both produce the same blank field. Both are consistent with one detection followed by 2 non-detections. The very pattern that the orbital models turned into a virtue, the appearing and disappearing on a schedule, is also exactly what a transient dust structure would produce by accident, with no schedule at all. The difference is that one of them keeps a promise and the other does not. A planet on the favored orbit is committed to a future position. It has signed a contract with gravity. It must be at a calculable point in the sky at a calculable time, or the orbit was wrong. Dust signs nothing. It can be anywhere or nowhere. It owes the next observation no particular outcome. And that asymmetry, The planet's obligation against the dust's freedom is the only thing that can pry the two explanations apart. That difference is the fulcrum the August 2026 test rests on. If S1 reappears precisely where the orbital models predict it should be, the dust hypothesis effectively dies. Dust does not follow a calculated orbital position to within measurable precision across 2 years. A planet does. If S1 does not reappear, or reappears in the wrong location, the dust explanation becomes not just viable, but favored. The team's own framing of the situation holds regardless of which outcome arrives. Even if S1 turns out to be something other than a planet, the observations establish what Webb's MIRI coronagraph can achieve at Alpha Centauri. They define the sensitivity flaw. They demonstrate the techniques. They build the framework for deeper searches that follow. The methods have all failed here in their own specific ways. One of them produced a candidate that could be a planet or could be dust. The answer to that question depends on a single observation still 14 months away. Whether the answer holds or dissolves, the methods are not finished with this system. Even if S1 is a planet, and even if August 2026 confirms it, what we will know then is still a fraction of what the system might contain. The confirmation would close one question and open a much larger one. And that larger question is structural. It is built into the instrument itself. There is something almost paradoxical in that. A confirmation is supposed to settle things. You search, you find, you verify, and the matter is closed. But a confirmed S1 would settle only the smallest version of the question being asked. It would tell us that one gas giant exists around Alpha Centauri A. It would tell us nothing about whether anything else does. And because of what S1 is, large and warm and bright by planetary standards, confirming it would actually sharpen the uncomfortable fact lurking underneath. It would prove that the system can hold planets, while leaving us blind to every planet smaller than the one we found. The win would double as a reminder of how much remains unwinnable with the tools in hand. Webb detected S1 at more than 10,000 times fainter than Alpha Centauri A. That sounds like extraordinary sensitivity. It is. But a gas giant is the easiest kind of planet to find. It is large, warm, and thermally bright in the mid-infrared. S1 sits near the edge of what Webb can reach. A Neptune-sized world around the same star would be significantly fainter. A super-Earth would be fainter still. An Earth-sized rocky planet would fall far below the detection threshold entirely. Not somewhat below, far below. No amount of processing, no refinement of the subtraction pipeline, no additional observing time would bring it into view. The instrument simply cannot reach it. Think about what that means in practice. There could be an entire architecture of smaller worlds orbiting Alpha Centauri A right now. Rocky planets. Worlds in the habitable zone where liquid water is possible. Worlds with atmospheres, with geology, with chemistry we have no access to. And every one of them would be invisible to Webb. Not obscured. Not at the edge of detection. Invisible. Below the sensitivity floor by a factor that no technique can bridge. The best way to feel the weight of that is to turn the problem around. Imagine an astronomer in the Alpha Centauri system. Imagine they have built a telescope equivalent to Webb. Equivalent optics, equivalent coronagraph, equivalent detector sensitivity. They point it at our sun, 4.3 light-years away. Our sun would appear to them as a bright, middle-aged G-type star, broadly similar to Alpha Centauri A, a reasonable target. A plausible host for planets. What would they find? With their MIRI equivalent coronagraph operating in the mid-infrared, they could, in principle, detect Jupiter. Jupiter is large and warm enough that its thermal emission would just clear the detection threshold. They would see a faint point source at roughly 5 astronomical units from the Sun. They might conclude that a gas giant probably exists there. Saturn would be harder. A marginal detection, right at the edge of what the instrument could achieve. They might flag it as a candidate. Uncertain. Beyond that, everything disappears. Uranus and Neptune would fall below the sensitivity limit. Earth would be thousands of times too faint to register. Mars, Venus, Mercury would vanish the same way. The asteroid belt, the Kuiper belt, the entire inner solar system would be invisible noise. The alien astronomers' census of our solar system would read, one gas giant, confirmed. One additional candidate, marginal. Everything else, undetected. That census would capture roughly 30% of our solar system's total planetary mass, and precisely 0% of the worlds where conditions allow liquid water to exist on the surface. They would not know Earth is here. They would not know that one of those invisible rocky planets has been running a continuous biological experiment for nearly 4 billion years. Not a hint of it. Not a signal. Not a shadow. The biosphere, 4 billion years of life assembling and diversifying and eventually building radio telescopes, would be utterly invisible to the most powerful space telescope ever constructed, pointed directly at us from the nearest star system. Sit with the specifics of that for a moment, because the scale of the omission is the point. Everything that has ever happened on this planet, every ocean that filled, every continent that drifted, every forest that rose and fell, every creature that lived and died, the entire human story from the first sharpened stone to the launch of Webb itself, all of it unfolded on a world that would not register as a single pixel in that alien census. The astronomer would log a gas giant at 5 astronomical units and a marginal second candidate, and then move on to the next star on the list, having no reason to suspect that the system they just catalogued contained the only known instance of life in the universe, and they would not be making a mistake. Their instrument would be working perfectly. Their analysis would be sound. Their conclusions would be the correct conclusions given the data they could gather. The failure would not be in their method or their care or their reasoning. The failure would be built into the physics, into the brutal contrast between a star and the small, cool worlds beside it, into the simple fact that the things most worth finding are the things hardest to see. They would do everything right and still miss us entirely. That is not an edge case. That is the situation. And here is where the mirror inverts completely. We are the alien astronomer. We are the ones on the other side of that 4.3 light-year gap. We are the ones pointing a Webb-class instrument at a sun-like star and reading the census. What we find is what they would find looking back at us. The largest, warmest members of the family. The rest, hidden. Even if S1 is confirmed as a gas giant on a stable orbit, everything smaller than Saturn around Alpha Centauri A remains beyond our reach. Everything cooler than a few hundred degrees is lost in noise. The worlds that matter most for questions about life, rocky planets in the inner habitable zone, are precisely the worlds we cannot see. Not harder to detect. Not at the edge of possible. Simply beyond the current frontier. The frontier will move. The Roman Space Telescope carries a coronagraph instrument designed to push contrast ratios deeper. Extremely large ground-based telescopes under construction in Chile will gather more light and achieve finer resolution than anything currently operating. A future mission concept called the Habitable Worlds Observatory is being studied specifically to image Earth-like planets around nearby sun-like stars, to detect them, and to measure their atmospheres for signs of biological chemistry. These are real programs, grounded in real engineering, but they are decades away. The Roman Space Telescope's coronagraph demonstration is a technology test, not a planet finder at Alpha Centauri's angular scales. The ground-based, extremely large telescopes will help, but the brightness and binary geometry of Alpha Centauri will remain a challenge at every level. The Habitable Worlds Observatory, if it is built and launched on a timeline that advocates are currently proposing, would be operational in the 2040s at the earliest. For now, we are limited to seeing the largest inhabitants. This is not a failure of Webb. Webb is doing exactly what it was designed to do, and it is doing it at the edge of what is physically possible given its aperture, its chronograph's inner working angle, and the fundamental brightness of the star it is studying. The point is not that the instrument fell short. The point is that the universe set a frontier, and Webb is standing at it. An alien astronomer with identical technology would not know our biosphere exists. We would never appear in their catalogue of detectable worlds. We would be one of the invisible ones, hidden behind the noise floor, orbiting quietly while they logged our gas giant neighbour and moved on. The same is almost certainly true of Alpha Centauri A. S1, if confirmed, would be the gas giant they can see. The rocky planets, if they exist, would be the ones we cannot. The system could be full, it could have an inner architecture as complex as our own. We would not know. We do not know. And with current instruments, we have no path to knowing. That is the census bias. It is not a problem that can be subtracted away or modeled out or solved with another observing campaign. It is structural. It is written into the physics of the detection method and the brightness of the star. What Webb has shown is not the system. It is the edge of what we can reach. And the edge, as it turns out, stops well short of the worlds that would matter most. It is worth being precise about why this cannot simply be engineered around. When astronomers face a faint signal, the instinct, the entire history of the field, is to gather more light, build a bigger mirror, expose for longer, stack more frames. Faintness yields to patience and aperture. But the census bias at Alpha Centauri is not a faintness problem in that sense. The rocky worlds are not merely dim. They are dim while sitting beside one of the brightest stars in the sky. And the limiting factor is not how much light you can collect, but how cleanly you can separate the planet's light from the overwhelming glare beside it. More exposure time does not improve that separation. It deepens both the signal and the contaminating background together, and the contrast ratio, the thing that actually matters, stays just as punishing as before. So the usual lever does not work. You cannot out-collect this problem. The planet's signal and the star's glare are locked in a fixed ratio set by physics, and no amount of staring changes that ratio. The only thing that helps is suppressing the star more aggressively, and coronagraph technology has hard limits on how deep that suppression can go before the instrument's own imperfections become the flaw. That flaw sits above the rocky planets. It will take a different generation of hardware designed from the ground up around this exact contrast challenge to push it lower. And even then, Alpha Centauri's particular brightness will make it one of the hardest places to do it. The question of what lies below that edge will outlast every instrument currently in operation. That question does not disappear when you change instruments. It deepens. What Webb showed was not simply that Alpha Centauri is hard to study. We knew that before August 2024. What it showed was something quieter and more unsettling. The edge of our reach stops short of the answer. And the distance between what we can see and what we need to see is not a gap that more time or more software will close. When people call the result disturbing, they tend to imagine something dangerous, a threat, a disruption. That is not what the word means here. The disturbance is conceptual. It moves slowly. It does not arrive with urgency, but with the gradual recognition that an assumption we carried without examining it has turned out to be wrong. The assumption was simple. Closer means clearer. This is embedded so deeply in human thinking that it barely registers as an assumption at all. We understand our neighbors better than strangers across the ocean. We know the terrain of our own backyard. We see nearby mountains in detail that distant ones cannot offer. The idea that proximity and understanding travel together feels less like a belief and more like common sense. It is worth noticing how rarely that assumption fails us in ordinary life, because that is why it runs so deep. Walk toward anything and it resolves into detail. The blurred shape on the horizon becomes a building, then a building with windows, then a building with a number on the door. Distance hides, closeness reveals. We have spent our entire evolutionary history in a world where stepping nearer was always the way to see more clearly. And the lesson is written into us at a level below conscious thought. Nobody teaches a child that approaching a thing helps you understand it. The child simply does it because the world has always rewarded it. So when the rule breaks, it does not break gently. It does not feel like learning a new fact. It feels like the floor shifting. The nearest sun-like system in the galaxy, the one we can almost point to, the one a century of dreaming has treated as half familiar already, turns out to be among the hardest places in the sky to read. And the reason is not distance, the enemy we know how to fight, but its opposite. The system is too close, too bright, too loud for the instruments we built to listen for whispers. The thing that should have made it knowable is the thing that hides it. But stars are not friends. In stellar astronomy, proximity brings brightness, and brightness brings glare. The nearest sun-like stars are not clearer targets. They are harder ones. The same closeness that makes them obvious to the naked eye makes them overwhelming to every instrument we build. Distance can paradoxically offer clarity. The farther star does not flood the detector. The answer was stranger than expected. The systems we know best are not the nearest ones. They are the dimmer ones. Farther out, easier to manage. TRAPPIST-1 sits roughly 40 light-years away. It is an ultra-cool red dwarf, roughly 200 times smaller than our Sun, and more than 2,000 times fainter. No unaided human eye has ever seen it, yet we know its planetary system in detail that Alpha Centauri cannot match. 7 rocky planets confirmed, 3 of them in the habitable zone. Webb is already performing transmission spectroscopy on their atmospheres, reading chemical signatures through layers of air we have never touched. That comparison should feel upside down, and it is worth letting it stay uncomfortable. TRAPPIST-1 is 10 times farther from us than Alpha Centauri. It is a star so dim that for all of human history, nobody knew it was there. By every intuition we carry about distance and visibility, it should be the harder target, the more remote, the less knowable. And yet we can name it 7 planets, place 3 of them in the zone where liquid water is possible, and sample the chemistry of their atmospheres. Meanwhile, the bright, famous century-celebrated pair sitting a quarter of that distance away has yielded not one confirmed world. The faintness that makes TRAPPIST-1 invisible to the eye is exactly what makes it legible to the instruments. Its dimness is a gift. The planets crossing in front of it produce clean, deep, repeatable dips in a manageable amount of light, and the star is quiet enough not to drown them. Epsilon Eridani is a K-type star at 10.5 light-years. A single star. No binary companion to contaminate the signal. At least one confirmed planet, a Jupiter-mass world orbiting at 3.4 AU. Detected through radial velocity. Confirmed astrometrically. Clean result. Tau Ceti is a G-type star, broadly sun-like, 12 light-years away. Single star, clean baseline. Multiple planet candidates in the radial velocity data, up to 4, though the count remains debated. Barnard's star sits 6 light-years out. A contested candidate planet emerged from 2018 data, still unconfirmed, but still closer to resolution than anything around Alpha Centauri. A Ross 128 at 11 light-years has a confirmed super-Earth in its habitable zone. GJ-A87 at 10.7 light-years has 2 confirmed super-Earths. The pattern is consistent. Single stars, even nearby ones, have yielded planets. Dim stars, even distant ones, have yielded planets. The one system that has resisted every method, every campaign, every instrument, is the nearest sun-like binary. We know the planetary inventory of faint red dwarfs 40 light-years away better than we know the inventory of the 2 sun-like stars sitting 4.3 light-years from our own front door. Our map of the local galaxy has a hole at exactly the most important address. Not a peripheral address, not a dim neighborhood we rarely visit, the nearest sun-like system, the place every interstellar mission plan begins. And here is the harder part. This is not a temporary situation. Better instruments will push detection thresholds deeper. 30-meter class ground-based telescopes are under construction in Chile. The Habitable Worlds Observatory, designed specifically for imaging Earth-like planets around sun-like stars, is studied for the 2040s. These instruments will see things Webb cannot, but the fundamental tension between closeness and brightness will not resolve. Alpha Centauri will always be one of the most technically demanding targets in the sky. The closest sun-like system will likely be one of the last we fully characterize. The August 2026 observation window stands as the nearest horizon. If S1 and Source C are the same world, the orbital models produce a specific testable prediction. The planet should swing back into a detectable position then, not approximate, not vaguely consistent, precisely there, following the arc of a calculated orbit. Stanimir Mechev, Canada Research Chair in Extrasolar Planets at Western University, has described this as the critical test. If the planet reappears at the predicted position, it would rank among the most significant discoveries Webb has ever made. What gives that test its force is how little room it leaves for ambiguity. This is not a search across a wide field, hoping something turns up somewhere. The models do not say the planet might appear in the general vicinity. They name a location, a small region of the detector where the planet must be if the favored orbit is correct. The observation becomes a yes or no question put to the sky. Look at the predicted spot. Either a faint point of thermal light is sitting there, within the tolerance the orbit allows, or it is not. There is no large grey zone in between, no room for a result that means almost anything. The prediction is sharp enough that the sky's answer will be sharp too. That is what separates the August 2026 observation from everything that came before it. The 2019 near detection was suggestive but isolated. The August 2024 Webb detection was striking but unconfirmed. The two non-detections were informative but, on their own, indistinguishable from an empty system. None of those individual results could close the question, because each was consistent with more than one story. August 2026 is built to do what the others could not. It is a prediction made in advance, on a specific orbit, at a specific position, with no freedom to be adjusted after the fact. The system has been asked to commit. Now we wait to see whether it keeps its word. Eric Gaidos at the University of Washington is more cautious. He has watched planet candidates come and go across the history of exoplanet science. Signals that survived one analysis dissolved under the next. The system's particular challenges make him reluctant to assign high probability before the prediction is tested. Both positions are reasonable. The science requires holding them simultaneously. What would confirmation mean? Aniket Sankhi, co-first author of the paper, has said that a planet's existence in this tight binary would challenge our understanding of how planets form, survive, and evolve in chaotic environments. Current theory predicts that the gravitational interaction between A and B truncates protoplanetary disks and destabilizes orbits beyond a few AU. A planet at 1 to 2 AU in the marginally stable zone, sitting on an eccentric orbit with inclination of 50 to 130 degrees relative to the binary plane, would mean that planet formation is more resilient than the models allow, more creative, more capable of finding paths that theory says should be closed. And a confirmed gas giant raises the next question immediately. Gas giants do not typically exist alone. What else orbits Alpha Centauri A, below detection? Rocky worlds, debris belts, ice-bearing moons, inner structures we cannot reach from here. The system could be full. If one gas giant survived in the marginally stable zone, smaller worlds at closer orbits might have survived as well in regions Webb cannot probe. If S1 is not confirmed, the blank spot persists. Even the most heroic coronagraphic effort ever aimed at this system could not resolve the question. The target is uniquely resistant. And the silence tells us something too. Not nothing, not absence, uniquely resistant silence. Either way, the result points in the same direction. The nearest sun-like system is not a familiar place we understand. It is an unresolved question, and better instruments do not simplify it. They reveal layers of complexity that cruder instruments could not even form questions about. The binary's geometry offers at least one narrow advantage. The angular separation between A and B follows their 80-year orbital cycle. At the 2016 minimum, they were separated by roughly 4 arcseconds as seen from Earth. At that distance, coronagraphic observations were essentially impossible. The two stars sat too close together for any mask to isolate one without the other's glare contaminating everything. By August 2024, the separation had grown to roughly 10 arcseconds. Enough room to work. The separation will continue widening through the 2030s and 2040s, reaching a maximum of about 22 arcseconds around 2055. The current decade and the next are the most favorable window in the entire 80-year cycle for direct imaging searches. We happen to be living in it. There is a quiet piece of luck buried in that fact. The 80-year cycle is indifferent to us. It was turning long before anyone built a coronagraph, and it will keep turning long after. For most of the 20th century, through the decades when Alpha Centauri loomed largest in the human imagination, when the mission concepts were drawn and the novels written and the games built, The two stars were sliding through the cramped end of their orbit, too tangled together to study even if the instruments had existed. The technology and the geometry were out of phase. We dreamed about the system precisely when we could least examine it. Now they have come into alignment. The instruments capable of attempting this exist, and the stars have drifted far enough apart to give those instruments room to work, and these two conditions overlap for the first time in the history of the effort. Had Webb launched into a sky where A and B sat 4 arcseconds apart, even its coronagraph would have been helpless here. Instead, it arrived to find the window open. That is not foresight. It is timing. We were handed a few favourable decades, and the question is only what we managed to learn before the stars wheel apart toward their distant maximum, and the easiest configuration slips away again. There is a broader implication that sits underneath all of this, quieter than the specific question of whether S1 is real. If the nearest Sun-like system can hide a gas giant in its habitable zone, then every other Sun-like system we have characterized across the catalogue of 6,000 confirmed exoplanets is even more incompletely known. Those systems are farther away, harder to study, observed with instruments that could not even attempt what Webb attempted here. If the closest target resists full reading, the rest of the archive contains hidden structure we have no current path to reaching. The galaxy holds something like 400 billion stars. Our census of what orbits them is a catalogue of the easiest signals. The most accessible addresses still resist full characterization. Think about what that means for the largest question. We are sitting on a planet orbiting one sun-like star, looking across 4.3 light years at another sun-like star, almost the same age, almost the same mass, almost the same luminosity, and we do not know what orbits it. We do not know whether our solar system is typical or exceptional. We do not know whether the conditions that produce life here are common or rare. Webb did not answer this. It opened the question wider. The system was named centuries ago. It was charted. It was written into mission plans and novels and games, and the default coordinates of 100 imagined futures. When we turned the sharpest eye ever built toward it, after all of that, it did not greet us with clarity. It offered a vanishing point of light and the suggestion that it has been keeping something from us. The house next door has rooms we have never entered, doors we cannot open, an architecture we are only beginning to map. The more carefully we look at Alpha Centauri, the less it behaves like a solved address. Proximity was never a promise of understanding. It was only ever an invitation to look more carefully. And we are just beginning to accept that invitation,